Hello guys, today we're going to be doing an experiment which is oxidation of cyclohexanol to cyclohexanone. Okay, the oxidizing agent is going to be sodium dichromate, and the reaction is catalyzed by acid, and what you end up with is Cr+3, which is very similar to a grand scale reaction of the Lucas reagent that we had last week. Okay, so as we said here, chromium, the oxidation state is +6. The chromium, the oxidation state here is +3. And we go from +6, we go down to +5, +4, +3, +2, etc., +1, 0, etc. So when we go down, this is called a reduction. This means the chromium +6 is a reduced itself. Therefore, it's an oxidizing agent. So as we learned in English 101, if you are active as an oxidizer, therefore yourself you get reduced, and that's the passive voice. So it's active versus passive voice. Now it's very easy to remember that this is a reduction, because an oxidation, because in oxidation you add extra oxygens or remove hydrogens. So in this case we remove hydrogen. Remember now there is no hydrogen here, there's no hydrogen there. So we end up with cyclohexanol. So therefore, cyclohexanol to cyclohexanone gets oxidized. Therefore, it's a reducing agent. On the other hand side, Cr+6 goes to Cr+3 again. And I'm sorry I'm repeating, but I'm too old. So this one gets reduced, therefore gets oxidized, oxidizing agent. The problem with this reaction is that the main problem is that everything has to be done at approximately 35 degrees centigrade. Not much lower than that, certainly not much higher than that. But it has to be at 35 degrees centigrade. Why? Because if you create any cyclohexanone, this one undergoes an equilibrium to the enol form, and then with the oxidizing agent of dichromate, you finish up with a product that is not what we want, okay, which is called adipic acid. Not adipic acid, adipic acid. So our job is basically, this will take place at higher temperature. Okay? Now if you do not keep it at 35 degrees centigrade and you leave it at say 0 degrees centigrade, what is going to happen is there will be a lot of it formed, and then the reaction will take off very fast as you go along, and then we will have a problem. We finish up with adipic acid. Again, our job is not to make adipic acid, our job is to make cyclohexanol. Okay, so what do? First of all, we will have two conical flasks. In one of them we will have cyclohexanol plus sodium dichromate, plus sulfuric acid. And the other one, you will have sodium dichromate. Remember we said when we talked about the Lucas reagent, this is orange, this is green. Okay, so what do we have in this case? We are going to have the cyclohexanol and sulfuric acid in here in ice. Now, when we say we have it in ice, this doesn't mean you make it sit on top of ice, right? We want to make sure the solution is cool. Now, you know, of course, from the Olympics, if we are on ice, we can ice skate, we don't get very cold, but if the ice breaks and we go inside the water, then we die from hypothermia. So therefore, what you need to do when I say in ice, we always mean ice, water, bath. Means ice and water. So you keep that solution there, all right? And then you start adding sodium dichromate dropwise, okay? But the temperature must be about 35 degrees centigrade. If it is too low, you take the conical flask out of the ice, and therefore this solution will warm up and keep on adding sodium dichromate. If it is too hot, goes way above 35 degrees, you take a couple of ice cube chunks and add them into the solution. Again, the whole thing of the addition of sodium dichromate shouldn't take more than about 3 to 5 minutes, no more than that. The temperature again has to be 35, then you leave it outside the ice bath for a few minutes, and then the temperature will go slowly. Now the solution originally is orange, it will turn into deep green, almost black, okay? And so therefore what happens now is that you have your solution here, and you let it sit there and it goes all the way to 40, 45 degrees, maybe 50 sometimes, that's okay. And then after that, it goes by itself down. When it's approximately 40 degrees centigrade, what you do is you set up a simple distillation apparatus. Remember now how the simple distillation apparatus is. We've done several of those, we'll do it again. And Dr. Shin will do the presentation for you. So we have the round bottom flask in the solution here, to which we add also some water as prescribed in the manual. The first thing you do is you clamp. Remember now, we try to make sure that we do not have the heating mantle here when we add the solution. Why? Because if anything gets spilled in here and you apply heat, you're gonna breathe bad vapors, and that's not very good. We want to see you next week, right? Okay, so we clamp it very, very well here. Then remember now, over here, we have the connecting adapter, and there are basically you have a joint here of the connecting adapter that has to be greased. Then we have the thermometer, and the mercury bulb, top of mercury bulb should be at the bottom of the conical flask, of the adapter, the connecting adapter. Then in here, of course, you have to have joint that has to be greased. And then over here now we have the condenser. And we collect everything in an ice water bath. Now, remember now water goes in from the bottom, out from the top. What are the joints you have to grease? The connecting adapter joint, bottom part, the thermometer adapter, and then the outlet of this connecting adapter. And remember now, we cannot put our finger there because it's gonna get stuck, and we don't wanna see that. I don't have time to take you to the emergency room. Anyway, we perform a simple distillation, and we collect the solution as prescribed. And then now there are some problems here.
Do we have to add the oxalic acid before simple distillation?
I forgot that. Sorry. Forgot that.
Right.
Okay,
Excuse me.
so in case now we have any extra dichromate, what we need to do is we need to add oxalic acid, which will react with excess Cr+6 and will destroy that to give you CO2 plus Cr+3. The reason is that we do not want any more further oxidation, and therefore what you're going to be distilling will be water, cyclohexanone, and maybe a little bit of cyclohexanol, although I don't believe there will be too much cyclohexanol since we have excess of the dichromate. So again, the purpose of the oxalic acid is to destroy the excess dichromate that we may add. You collect the solution in ice, and then now we have to basically make sure that the solution gets purified. So we will have two layers. The problem, unfortunately, is that cyclohexanone, here now what we're going to get is cyclohexanone plus water. Okay? So then what happens now, both of them happen to have a density that is very close to 1. And so what we need to do is we need to have a good separation. And so in order to do that, what we do is we have something that is called the salting out effect, which means we add pure salt into the solution that we collect. And what is going to happen now, the density of water, because you add salt, is going to be higher than 1.0, which means that the cyclohexanone is not going to react to sodium chloride, because sodium chloride is ionic, right? So water will react to the ionic compound, will make a solution of a density that's higher than 1, and cyclohexanone will be less than 1. It will be less than that of the salt solution.
0.95.
And therefore what we do then is 0.95, as Dr. Shin says. We will have to have a separatory funnel. We will add the solution here, and we will have to have a conical flask where we separate. Okay? Now, the bottom part again, as we said, is the water layer. Why? Because we add the sodium chloride, right? So the solution is heavier than 1.0, so it will come down. Cyclohexanone, which has a density that is just below 1.0, is going to be on top. Now remember, now we have done separations before. When we do separations, there is a blind side, which is usually here at the bottom of the separatory funnel. And so therefore what happens is you will separate these two layers. However, it is unfortunate and inevitable that some of the water will be left, and therefore the cyclohexanone is not going to be absolutely dry. And so therefore what we do is we separate them now in two layers, in two different solutions. This is the bottom layer, which is the sodium chloride and water. Then we have the top layer, which is cyclohexanone plus maybe some water. Okay? Now what we need to do then is we need to dry it, and the way we do it is we add sodium sulfate. So we don't need to weigh exactly a certain amount of sodium sulfate or magnesium sulfate depending on the dehydrating agent. It doesn't really make a difference. You add a little bit of a tip, and when you add it there, what's going to happen is you will see the solid going at the bottom, and it's going to be wet, sticky. This is because it absorbed all the water. Now this dehydrating agent is very, very similar to what happens in the winter. In the winter, we know that we use calcium chloride to basically melt the snow when it snows. But what we have in this case is, if you leave that calcium chloride over the summer and then you go next year, the year after you'll find out that the beads are not clear beads anymore. They're actually sticky beads. And the reason for that is that they absorb water from the air. And basically this is what the sodium sulfate or magnesium sulfate is supposed to do, which makes them a good dehydrating agent. You will get the organic layer here, and then you filter it via, not vacuum, gravity filtration, which means you take a funnel, put the filter paper, put the filter paper on it, pour the solution on top, and connect it into a round bottom flask that is dry. So one of you is doing this extraction, and the other person cleans up the distillation setup that we had before. It has to be absolutely dry, which means you wash it with water, you rinse it with acetone, and then it's ready to go. Then you perform a simple distillation apparatus. Remember, in this case, and in the second distillation, we always use boiling chips, remember that. And then we are going to have a distillation, basically, that you collect your cyclohexanone on a pre-weighed vial, which means your vial, your container where you collect it, is going to be dry, and you have to know the mass when it is empty. After that, when you have your cyclohexanone, you dry it, and you go and reweight and find the difference of cyclohexanol you produced. So the question is, how do we calculate the percent yield? So the percent yield will be as follows. We have cyclohexanol plus the sodium dichromate in acid will give you cyclohexanone plus Cr plus 3. Now don't worry about the oxidation reduction reaction. What we know is that this one is actually in a little excess. How do we know that? We know that because remember we added oxalic acid, and the purpose of the oxalic acid is to destroy the excess of dichromate, which means that this one, see, if this is excess, this is something we call the limiting reagent. And for those people who don't remember this, let's put it that way. Suppose say you go to a party and you have 10 boys and 12 girls. You're not supposed to go to parties anyway because you're supposed to be doing homework, but that's another story. So you have 10 boys and 12 girls, and assuming a boy dances with a girl, how many couples you're gonna get? Of course you know, 10. What's gonna happen? The two girls are going to be by themselves talking about I don't know what. Nothing but chemistry, of course. But anyway, so we have now the limiting reagent, which is what is the minimum, the least reagent. And so the molecular formula for this is C6H12O, and the formula here will be C6H10O. Okay? Assuming we got a mass, I don't remember the exact mass, but suppose that we got approximately say 5.0 grams of this, and we isolated 4.0 grams of this. The molecular weight of this will be 72 plus 12 is 84 plus 16 is 100 grams per mole. This one will be 72 plus 10 is 82, and 16 will be 98 grams per mole. So the number of moles you got here will be equal to a 5.0 over 100, which is equal to 0.05. And the number of moles you got here will be 4.0 over 98, which is going to be approximately 0.04. Okay? Forget about the significant figures for now. Now remember now, according to the equation, one of these gives you one of these. This means now that the expected yield will be 0.05 moles of cyclohexanone. Why? Because 1 gives you 1. And since we start with 0.05, we should expect to get 0.05. But this is expected yield or theoretical yield. But the actual yield, which is actually what you did in the experiment. And why this takes place? Because you had a lot of transfers. You had a lot of side reactions that took place. And so therefore, in this case, expected yield, the actual yield will be 0.04 moles of cyclohexanone. And so therefore, the percent yield will be equal to 0.04 over 0.05 times 100, which is going to be 80%. So far, so good? Any questions? So now Dr. Shin, who is now the photographer, is going to be actually the person who will be performing the experiment. And then we will edit this thing and we will place it online. And you can have a link again and watch it. And remember now you have the pre-lab and you have the lab report. And I'm going to send you again directions, so pay attention to your email. All right, I'm using the emails that appear on CUNY First. I don't know what your private emails are. Whatever is there, that's where I send you the information. So hope you understood this whole thing, and we will cover part of it in lecture in Organic 2, and Dr. Shin and Dr. Zhu will go over them in 128. Okay, thank you.
Okay, first we got 10 grams of cyclohexanol, hexanol, which is frozen already. So I make a 0 in the aluminum flask. Okay. 10 grams of cyclohexanol and then add 40 grams of ice inside. Okay, 40 grams of ice and then we add sulfuric acid here.
Sulfuric acid. We add in, then we leave it with sulfuric acid. Then we will add the sulfuric acid again against the walls.
And then make the one. And then we prepare 11 grams of oxidizing agents, which is sodium dichromate. So I'm using the beaker here and make 0. Then add sodium dichromate until it becomes 11 grams. Yeah. Yeah. Okay, 11.04, 11 grams. And then we will adding the water to dissolve it. Okay. 50 ml of this water. We just stir until all dissolved. And we're adding this solution to the mixture of cyclohexanol and sulfuric acid with ice. We were stirring with thermometers because we have to monitoring the temperature. As Dr. Spano says, we cannot go over 35 degrees Celsius. So maybe one person stirring it, one person adding this dichromate. Yeah, all dissolved. So I'm adding, and the Dr. Spano, we're stirring as monitoring the temperature. And don't drop it on his hands because it becomes aged. Aging is the oxidation process.
Checking the temperature. The temperature as we see it now, it's about 10 degrees, so we can take it out. Because remember now, we have to keep it at 35 degrees. This is about 10. Okay, so we shake again. We shake again. And the temperature is about 5 degrees, so we have to keep on. Just have to let it go a little further. Because if you keep it at 0 degrees centigrade, what happens is it stays there and then the reaction takes off like crazy. Still 5 degrees.
Color change to brown.
Still about close to 5 degrees. Okay, and a little bit more.
can see the flask.
Okay. You see the flask, guys? Okay.
What's the temperature?
The temperature is about 10, so we still have to swirl and keep on adding more.
So we have to add all of this to the dichromate,
Yeah.
which is excess.
It's about 16 degrees.
Okay, it's very hot.
Okay, can add a little bit more now. Okay, looking good. Can you see it, guys?
Yeah,
Okay, no more texting.
Color is changing means the oxidation is happening, but it's not completed.
Yeah. So you see the green color formed, right? It looks black because you have a combination of green and orange. So, but if you put a drop of it in a filter paper, it turns out to green. Okay. So now we have about 25 degrees.
Okay.
Okay, can I add a little bit more? Okay. Now the temperature is very close to 30 now, so we have to get ready, right?
Yeah.
Now you see the color here, how more green it becomes, right?
We put into the ice press.
Yeah, we have ice. We can use the ice cube from here. There's no problem. Okay. So this is about 32 degrees now. It's okay. We'll add both ice. Keep on it. It's about 31 degrees. Okay. I'm gonna give it a boogie here. Now it's very close to 35. So if you want to cool it down a little bit, still 35, that's okay. Still 35, 36. It gives too much. You know what the heck, you know, you add a little bit of ice cubes here. That will cool it down and will dissolve it. And the temperature now goes down to 35. A little bit more, just to be on the safe side, because okay. Again 35.
Inside?
Yeah, we can add.
So put it inside so I can let you know.
Okay.
Yeah. Just lay them.
Come on.
Okay, your fingers.
Oops, sorry, my friend.
Don't be aged.
Okay. We almost drowned the conical flask there.
So colors keep changing.
Yep, it becomes greener and greener, right? Now it's 30 degrees, so we can add all of it, the rest of it, right? According to the procedure, you add the last 2, 3, 4 milliliters. Okay, it's still 30. Keep on adding all of it. Okay? Because we're at the end of it.
Yeah, because the dichromate is excess, so at this point, oxidation is almost completed.
We're still at 35, exactly, on the money. Okay, as you see here, we go 36 degrees. We added all of it. We let it, give it a boogie, as we say. We let it sit there for a while, and goes up higher. Can be up to 50 degrees. Try not to do more than that. Okay, so it's exactly 40 now. So we can cool it down a little bit, just for the heck of it. Shake it up again. And that's 40 degrees. So theoretically it can go up to 50 with no problem at the end, you know, because all of it has taken place. Dissolving has taken place. We keep on swirling it. Okay, just a little bit higher than that. So if we pull it down. Now, as you see here, the color changed to green. You see that? There's no more orange there, right? And it's going down to 45. So when it reaches approximately 40 degrees, we are ready to add the oxalic acid. And the oxalic acid will give you carbon dioxide, so you will see some bubbles coming out. What's the purpose of the oxalic acid again, as we said? To destroy the excess dichromate. Okay, so now we are very, very close to 40 degrees. That's good enough, so we can add oxalic acid in a couple of minutes. To be patient. Dr. Shin, do you think you would like to pour the oxalic acid while it is in the round bottom flask?
Yeah.
Okay. So what we can do now is, I think we're very close to 40 degrees. You want to pour it directly there and then add oxalic acid on it? It's up to you.
Yeah.
Okay.
Because it makes bubbles.
Whatever you say. Go ahead.
So this is 1 gram of oxalic acid.
Okay. What's the purpose of it again? To destroy the dichromate. So you see bubbles coming out, right?
But I don't want to all at once because sometimes there are too much bubbles. So I go half first and see how much.
See the bubbles coming out? Give the boogie again.
The CO2 gas is the oxidation product of oxalic acid. And
Okay.
I'm pouring the rest of it. Okay, 1 gram is added.
And now we are ready for the distillation. Now you see more bubbles coming out. Do you see that? Do you see the bubbles here, right? This is the carbon dioxide. This means we had excess dichromate, yes? Excess chromium 6. Okay?
So you have to start at
Which
the-
of course matches what we said, that one cyclohexanol gives you one cyclohexanol, and therefore all the calculations for the percentage yield are justified to be on a 1-to-1 ratio. So cyclohexanol to cyclohexanone is the limiting reagent, okay? Dichromate is the excess, which we destroyed by means of oxalic acid. So far so good? Okay, ready for distillation?
we have to wait until no more bubbles. Because
I
bubbles
think
is-
when you leave it open in a large surface, go away. Okay? Can you make it? Great. Okay, notice again what Dr. Shin did very correctly. He took the round bottom flask. You notice he did not put the round bottom flask directly on the heating mantle. Why? Because if something falls on the heating mantle and when you perform a distillation, it will burn, and therefore that's not very good for your health. Okay? The temperature is approximately close to 44 degrees. So I guess we can think if we have to push the heating. One second. Here we go. Ready to go.
Okay. Okay, so it's done. So we transfer this mixture to 250 ml. to rinse out, we add 30 ml of
Water.
this water.
So we can transfer all contents, right?
Almost nothing remaining, but
Yeah.
it's a little bit yellowish.
You lucky guys, we have to wash the dishes. And there's no dishwasher here.
Okay.
Take it. Wash it. Yeah, give me that one to wash.
Okay, now we set up this image. So first, position the flask. Okay, touch the bottom, touch the wire. Okay, the boiling tube is inside. Okay, and the next, connect the three-way adapters. Okay. And as Dr. Borsagono says, you have to greasing it. So when you grease, okay, three position, a little bit, don't use too much. 1, 2, and 3. Okay, always you have to greasing to the male side. Okay, then put here and spinning it. So the grease is spreading. And then condenser. Again,
the thicker
the
condenser.
steamer.
You can use the thicker condenser. It's okay.
Connect. Spinning it. So grease is spreading, and usually they are not easily off. But to make sure it's not falling out, we connect.
Usually we put more than one rubber band because the rubber bands are beat up, you know.
It's not falling out. Thermometers and adapter. 1, 2, 3. Again, spinning. Okay, and position the top of the blue part of thermometers is just bottom of the side. Okay.
Put more than one rubber band.
Yeah. Why is it?
Because it breaks down all the time because they're so old.
Back monitor. Maybe we can put insurance. The receiving flask. Okay. Water in, water out. So using the water tubes. Water going in from the low place and out to
This way. We put it this way so this way we don't splash each other and start using 4-letter words, right? And you have to go to church for confession before using bad words. You wanna clamp it?
what's happening. When you turn it on, do it slow, watching it. Because I don't want to have a shower during the winter time. Okay. Opening out. So it's set. Now set to heating. The boiling point of cyclohexanone is about 156, 150, so it's very high, so we set 9. And waiting. And since you isolate the product during the distillation, you have to record it which temperature ranges, you collect your distillate. So distillation is going on, but it's not boiling yet. Really. Okay, solution is boiling now.
And it's dripping.
And dripping. Okay, yeah. Can you see this is dripping? Okay, yeah. What's the temperature? It's about 98.
Because mostly it's water.
Yeah. 98 degrees Celsius. So yeah, because the mostly water comes together with cyclohexanol.
That's right. As is you do.
So temperature 98 degrees Celsius. You got the first few drops. So you have to recording it. And it's keep boiling. Oops. And keep collecting. So since it takes too long, I will stop here for a while until we got everything. Okay, distillation is keep going and already enough. Product is forming. Actually, that's the mixture of the water and cyclohexanol product. And what's the temperature? We got the first drop at 98 degrees Celsius. Now it's 105 degrees Celsius. You cannot see because it's not clear, but 105. It's a little bit higher than the water because distillate of water and cyclohexanol come together. As you see, the solution now changed to green colors. Okay, remember chromium 3 plus become green colors. Okay, it's still boiling, so we have to wait until boiling stops, and we walk out with distillate. So you have to recording which temperature ranges. We collect the distillate, which is 98 degrees Celsius to 105 degrees Celsius. So clearly writing on your result site because that's one of the data. Okay.
Okay.
So we got the distillate.
Okay, we need a funnel.
Go.
So here's the distillate. Okay, and you see the densities are very, very close to each other. So in order to make sure that the separation takes place, what we do is we add sodium chloride. Okay. And we shake it up, shake it up, shake it up until the bottom layer is saturated. And now you can see the separation much better, right? Do we see that? Oops, you don't see it.
Okay.
Here we go. So you see at the bottom we add the excess sodium chloride, okay? And so you at the bottom, now the bottom layer is a water layer. So we decant everything in here. And we have now two layers. You see the bottom layer, the cloudy layer, is the water layer with the sodium chloride. It's okay. It's okay. And the top layer is a clear layer. The clear layer does not have any salt in it, right? That's why it's clear. The bottom one is saturated salt solution. All right? And now we're going to separate them. Okay? So the way you separate it is again this way. Again, the bottom layer is not what we want, right? It's water, right? Which has a lot of sodium chloride. And I said, the blind side, when you do a separation and you drive a car, there is a blind side, right? The blind side is here. So what we're gonna do is we are separating it slowly, very gently, drop by drop, drop by drop. Okay, So here's my cyclohexanone. But my cyclohexanone now may be a little bit wet too. Remember, cyclohexanone has C double bond O. C double bond O has a pair of electrons. It can hydrogen bond with water, right? So what we want to do now is we want to make sure that this is dry before we do the final distillation. And so therefore, as a result then, what we're going to have to do is we will add the sodium sulfate. So we have a conical flask here. Now this is a water layer with the sodium chloride. We don't care so much, we don't care at all about it. So we pour the solution here of cyclohexanone, right? Now remember now, it's probably a little bit wet. And I can see it's a little bit wet because you may see a drop or two of water there, but that's okay, we'll take care of it because Dr. Shin now, with his magic hands, is adding sodium sulfate anhydrous. Come on, Jesus, let's go. So he's,
Oh, there's some
you
water.
see how wet it is now?
Big chunk.
Big chunk of water, right? So we add a little bit more. Let it sit there for a couple of minutes. I'm going to get a funnel. Filtration, right? Dry funnel. Yes?
No, we don't.
Okay.
Yeah. So we'll leave here for a couple of minutes.
Mm-hmm.
Maybe we can decant.
Okay. Okay. So now this one can be washed. This can be washed. This can be washed. This can be washed. This one we don't need. Bowling chips go back to where they came from. Stop.
Now it's enough time passed, so we'll get the mass of the products. So put the small beaker, make it 0, and we decant.
Notice now what Dr. Shin does. He keeps the solid back, right? So he decants. This means keeps the solid back in the conical flask and the liquid goes into the beaker.
And this is the tips. Using the pipette, we can extract more liquids without solids. No solid.
A little bit more liquid here. Okay. So we're ready to go. So how many grams did we get, Dr. Shin?
We got 4.09 grams, but to make sure, I will show you.
4.19.
4.09.
09. Say about 4.1.
Yeah.
So basically, as you see, we didn't get 100% yield because there are so many other things that take place, including distillation, the filtration, the decanting, and all these other things. And so what we're going to do now is we are basically be able to get the percentage yield based on the fact that we created 4.09 grams. Now, you know how much we started. You can do the calculations based on whatever I told you about calculating percentage yield, and then you can add these in the report. Okay, if you have any questions, email us and we'll be more than happy to respond to you. Dr. Shin, anything?
Nope.
No? Okay.
Okay, bye.
Enjoy the day. Don't forget the homework.
Okay.